Okay, so welcome everybody to the lecture 4 of this differential geometry series or topology series, whatever you might call. So let me start by again recalling what we have seen as the definition of Gaussian and mean curvature. So for a point P in a oriented surface S, we have the map Weingarten map, which we now just will say without loss of generality as W. This is a map from the tangent plane to the tangent plane. And we know that this is a linear map. So we have defined the Gaussian curvature as the determinant of the Weingarten map and the mean curvature as half of trace of the Weingarten map. And this we have already remarked that this we can do because this guy is a linear map. It's like a linear map from a vector space kind of thing. And then once you have a linear map, then you can define a matrix associated to some basis. Here we can take, for example, the basis corresponding to the tangent vector. And then you can define the determinant of the matrix. Okay. So then we have also defined a symmetric matrix corresponding to the first fundamental form, E, F, G, and F double I, which is corresponding to the second fundamental form. And we finished with the statement of the proposition, which gives us actually the first step towards explicit computation of the Gaussian and mean curvature. So what's the proposition? So the proposition says, let sigma be a surface patch of an oriented surface S, then the matrix of the Weingarten map with respect to the tangent vector basis sigma u sigma v of TPS is given by Fi inverse F double I. Yeah. Okay, so that was the proposition. So once we will have this, then our hope is we can just apply the definition of this matrix, and then we will find some explicit formulas for computing the Gaussian and the mean curvature in terms of the coefficients of first and second fundamental form, which will be then, we'll see in some examples that it's then easy to compute. Okay, so this was till yesterday, the last talk. Okay, so now let me continue to the proof of this thing. So the proof, So let me recall you something which we have already seen actually. So let me go to the second fundamental form notes. So here there was, this proposition. So this is already uploaded online. So that when we prove that this the second fundamental form's first definition and the second fundamental form's second definition, they are equivalent. So in course of the proof, we actually proved this relation that if you apply the Weingarten map on sigma u, then you get minus nu. N is the unit normal. And similarly, if you apply W of sigma v, then you get minus NV. So this was nothing. I mean, that's the proof actually. I mean, you just take the definition, you differentiate of the Gauss map, and then automatically you get this. Okay. So I am going to use this. So we have seen that W of sigma u is minus nu, and W of sigma v is minus nv. Okay. So this is like an image of the basis in the TPS. So once you know the image of the basis, I mean like image of the linear map at the basis elements. So then if we assume the matrix of W is A, B, C, D, then essentially what are we saying? So we are saying then minus NU, this is nothing but A sigma U plus B sigma V, and minus NV is C sigma U plus D sigma. That's the definition of the matrix of the linear map. Right? That's nice. So now it's kind of this, I guess, or I hope at least you should get the usual technique of proving something, because the definition of the second or the first fundamental form, these are like dot products with the sigma u, sigma v. So what's the natural way then? Then we will again take dot product. So essentially we take dot product of above equations with sigma u and sigma v. So this gives you, the first is minus L, I'm sorry, L. This is actually minus NU times sigma U. This is also another relation what we have seen. Let me again show this also. Yeah, here. This here. So what is the proposition? Ah, yeah, exactly. So NU dot sigma U is minus L. And similarly, NV sigma V is minus N. NU sigma V, NV is, that's minus N. Okay. So L is actually minus Nu dot sigma U. And now if you take dot product of sigma U with sigma U and sigma V with sigma U, this is nothing but now the coefficients coming from first fundamental form. So this would be what? A, now sigma U dot sigma U, but then that's actually nothing but AE. And then B, sigma U dot sigma V, that's nothing but F. And similarly here you get M is again minus Nu dot sigma V, which you can now rewrite as AF plus BG. So this I have completed the dot product of this equation with sigma U and sigma V. Now I'll do the same technique with the second equation, and that would give me the rest of the coefficients. So I will again get M is CE plus DF, and N is CF plus DG. So now if you see all these four equations simultaneously, this you should be able to now figure out or to write this in a matrix terms, right? So let me write this down. This is nothing deep. So you get basically L, M, N. This is E, F, F, G times A, B, C, D. So I rewrote these four equations in terms of the matrix multiplication. right? That's just as easy as this. But this gives me, so this implies fi f double I, this is nothing but fi times this matrix A, C, B, D, and this implies the matrix is nothing but fi inverse f, and this we are done. So I'm just taking the inverse to this side, and then that's the relation we wanted to prove. I mean, that's the proposition, yeah, that fi inverse f double. So we are done. I mean, this kind of relation, you should remember yesterday also when I was proving this Gauss relations. This is the same technique. I mean, it's, you should just assimilate it. I mean, this, you always have some, I mean, first you find some unit normal or some vectors, you rewrite as a linear combination of the basis vectors, and the basis vectors are the standard ones like tangent vectors. And then since the definition of the first and second fundamental forms are given by the tangent vectors, either dot product or double dot, and then you just use those relations to get relations. And luckily this gives us a very nice relations that the matrix is given by fi inverse f double. Okay, good. So once we have this, then we can get a very nice corollary. I am saying nice because this will enable us to compute many different Gaussian curvatures explicitly. So you can get the Gaussian curvature K. This is nothing but ln minus m square divided by eg minus f square, and h is lg minus 2mf plus ne divided by 2 eg minus f square. Now, if you remember yesterday's Gauss equations, there also I told you that this term regularly will come in the denominator. Why? Because let's see the proof. So what is the Gaussian curvature? By definition, this is determinant of the Weingarten map. And now already we have seen from the previous proposition that this is nothing but determinant of fi inverse f double I. And this is what? Then determinant is multiplicative, right? So this is given by determinant of fi by determinant of fi. And if you remember what was fi, fi was EFFG, and F double I was LMMN. So now this is immediate, right? This is what I want to prove. I mean, and that's kind of obvious. There's nothing mysterious about it. And that's exactly what I was saying. So this determinant of fi, this is actually coming here also. And that's what, again, you will see. So this is done. This we have already obtained. So the main content is actually already available from the previous proposition. This is just, I mean, that's what we are computing essentially. And this is okay. And what is H? So H is what? H is actually half of trace of fi inverse fi. So that means what? We have to somehow find out what is fi inverse. Now again, it's like the matrix algebra. If you know what is fi, then you know what is fi inverse, right? This is 1 over determinant, like so 1 over eg minus f square, and then you can compute the inverse. So that's actually Very simple. G minus F E. And so this implies Fi inverse Fi. If you multiply the two matrices, then you get 1 over Eg minus F square, and then Lg minus Mf, Mg minus Mf. I'm not even asking you to help me with this because these are just matrix multiplication. I really don't think this is something that illuminating, but the interesting part is you should understand, since it is a linear map, the whole content is already contained in the map itself, and since we can express the map in terms of matrices, then we can compute it. That's the beauty of the expression. And this is Ne minus Mf. So once you have this, then you just compute the trace. So you just take the sum of this and then half of this, and then we are done essentially. You can just finish this. Here's Lg minus Mf. I mean, you could see minus Mf, that's 2 minus 2 Mf, so that's minus 2 Mf, and Lg and Ne are here, Lg and N. And this is the coefficients from the front, so this is here, and 2 is coming basically because half of trace. Okay, that's easy. So, but even though that's easy, now it gives us a very nice formula for computing the Gaussian curvature and also the mean curvature, because we have already seen many examples where we have computed all of this, right? Also the first and the second fundamental. So let's compute for those same examples again. I mean, let's try to do this. So let me first take the example of the surface of revolution again, because that's a nice example always to take, because it's a general one and then you can specialize to several examples. So I am again considering, so consider the surface of revolution given by the surface path sigma uv is nothing but fu cos v, fu sin v, and gu. Also assume that fu is greater than 0 everywhere, and the planar curve given by fu and gu is unit speed. So f naught square plus g naught square is 1 everywhere. That's the exact same condition we took also when we computed the second fundamental. So we have already seen E is actually 1, F is 0, and G is F square. This we have seen last week. And this week we have seen L is actually given by F dot G double dot minus F double dot G dot. M is 0 and N is F G dot. Yeah. I mean, you could go back and check. Let me see if I have the examples here. Yes. Yeah. That's exactly what I'm saying. So that's the L. M is 0. M is 0. And N is F G dot. That's not difficult. So this is what we have written. But once we have all these 6 coefficients, now we can compute the Gaussian curvature, right? So the Gaussian curvature, K, this is given by, what was the formula? The determinant of both the matrix. I mean, ratio of the determinant of the both the matrix. So ln minus m square by eg minus x square. If you put all the value, this you get f dot g double dot minus f dot f double dot g dot, and here you get f g dot, and in the denominator you get just f square. So this is nice, but one can actually simplify the equation using this relation. So let's try to do this. So what we have that f dot square plus g dot square is 1. So which implies if you differentiate, then f dot f double dot plus g dot g double dot is 0. So now we will use this relation inside this and hope that maybe it will simplify, and it will. So what we are going to do, you just put f dot g double dot minus f double dot g dot and take just the g dot. So what is this? Now if you write this, or if you expand this, this is happening what? F dot and then g double dot g dot, right? So these two are same, I mean united. Then you have g double dot g dot. This you can replace as minus f dot f double. So let me do this. So this is f dot g double dot g dot minus f double dot g dot square. And now this I will replace by minus f dot square f double dot minus f double dot g square. And this is now what? Here now you take, I mean, it's like a linear calculation, minus f double dot, and now you again get f dot square plus square. So this is minus f double. Okay, that's quite nice. So then this gives you the Gaussian curvature is given by k is minus f double dot times f divided by f. So which is nothing but minus f double dot by f. Okay. It's okay, right? It's clear. Okay. So once we have computed this, so the formula is now very simple. I mean, the k is given by essentially ratio of f double dot and f along with a negative sign. So now let's see some special cases, as we have also done in case of second fundamental. So first we will consider some kind of a plane. Yeah, so let's consider the xy plane, for example. So if you take the curve gamma is u0, 0, then the surface of revolution associated to this is xy plane. So here you are taking fu to be u. So here you have taken fu to be u. So this implies what? F dot is 1 and f double dot is 0. So this implies k is 0, which is okay. I mean, the Gaussian curvature is ultimately a measure of how the curve is essentially, how the surface is curved. So it makes sense. Curvature is 0. Now let's consider the next example of the unit sphere. So we consider for unit sphere. So then what you put, fu is cos u, but this will give you f dot is minus sin u, and f double dot would be minus cos u, and this will give you the Gaussian curvature is minus f double dot divided by f is nothing but minus cancels out, cos u is 1, which is again nice, right? Because in case of unit sphere, we expect the curvature to be 1. which we have also seen before also. So this also makes sense. So this is nice. So we take the, we are done with the first example. So let's now consider some different example, which is also, I guess you have seen sometimes in the lecture. So what we will consider is, we will consider a ruled surface. So we just take like this, that's the gamma, and you take a point here, you take E, and then this you can take as delta. So what I'm taking, so consider a surface patch of a ruled surface by sigma uv is given by gamma u plus v delta u. Okay, so essentially what I'm saying is, this gamma u is essentially here, and gamma u will be this point, and then delta is this one, this direction, and then v is some arbitrary. Okay, nice. So once you consider this one, then again we compute all the derivatives along the tangent line. So essentially, what is sigma u? So sigma u is gamma dot plus v delta dot. Sigma v is actually nothing but delta. So this implies sigma uv is actually delta dot, and sigma vv is 0. And this will give you n is sigma u cross sigma v divided by norm sigma u cross sigma v. And this is the unit normal. So then m is actually given by sigma uv dot n. This is delta dot n, and the coefficients of the second hundred small n, like without bold, normal n is also 0. This you also can compute. So finally, putting all things together, you find out the Gaussian curvature k is nothing but ln minus m square divided by eg minus f square, which is nothing but minus delta dot n square, and below here. So essentially, this is always lesser equal to 0. Yeah, right? Because this is a always negative number, and this is also determinant is positive.
Sir,
Yeah.
for ruled surface, the Gaussian curvature is equal to the curvature of the curve gamma.
That's a good question. So, so what you are asking is k with so the question is whether k is equal to the curvature of gamma, right?
Yes.
And so let's see. So what is curvature of gamma? So curvature of gamma. So that's the question. So let's try to answer this. So tell me, what is the curvature of gamma? How do you compute this?
Gamma double dot norm of
Yes.
gamma double dot.
Yeah, so it's like norm here, right?
Yes.
So what is this? We have here we have not really computed gamma double dot. Did we? No, we didn't, right? Yeah, so this is at least from first instance, it doesn't look like, right? So what is gamma double dot here? For the rule surface, the problem is how the way I have taken the patch maybe it's not the best one to compute the curvature, because I think you have already computed the curvature of the rule surface, no? I mean, in the first week itself.
Yes, sir.
And what was it? I mean,
Uh,
because here, at least from the geometric thing, how you are considering the curve here, I mean, for the curve here, and when you consider the curvature here in terms of tangent vectors, or like in terms of the rate of the change of the magnitude of the tangent vectors, it's not exactly immediate, right? I mean, why it should be true. But I mean, since I don't vaguely recall, I mean, I don't remember this calculation, but you should definitely be able to do it now. I mean, just check the computation of this one and then compare with this one. Okay. So this should be, yeah. But yeah, that's a good question. I don't recall now itself at least, but yeah. And if not, I'll then come back to it. Okay.
okay, sir.
Yeah. Okay. So let's come back to what we have seen, that k is always lesser equal to 0, and that's the thing I wanted to conclude, that the Gaussian curvature of a ruled surface is always negative or 0, because it's lesser equal to 0, right? So this also you can actually think of when the 0 is attained, and this is also easy to see, because then you would have the 0 as the denominator, and then you should be able to find it. And we will actually come to some classification of surface later, and there also you would again see, I mean, somehow there also we would consider this kind of equation, like the curvature, the Gaussian curvature k somehow should determine the shape of the surface, and that will also determine how the shape looks, and this kind of classification we will come in the next lectures also. And there, so this ruled surface, and also, for example, the surface of revolution, or like the plane and the sphere, these are like kind of building blocks. So these examples, in many cases, maybe those are the only examples, if you assume some more conditions, of course. So it's an important example in some sense. Okay, so now what we see, that we can compute the Gaussian curvature, but like the calculation of, like the determination of k depends on derivative of the Weingarten map, right? Because Weingarten map is itself, so on, no, this is a wrong statement. What I mean is on derivative, because of this depends on derivative, right? So what I'm saying is, Gauss actually came up with some idea that to compute the Gaussian curvature, I mean, of course, he didn't name Gaussian curvature, he was saying, I guess, curvature. I mean, so he wanted to compute the Gaussian curvature intrinsically in some sense. I mean, like without going through the derivative process. So again, let me try to motivate you to through the curve case. So what I'm saying is, so again, let's again recall for a curve. So let's say if gamma is a unit speed plane curve, then we have defined its sign curvature kappa s, and we have shown that this kappa s could have been also obtained as phi dot. What was phi? Phi was this turning angle. So in other words, where phi was the angle between the tangent vector gamma dot and a fixed direction. So in other words, what I'm saying, the signed curvature of a planar curve, signed curvature is the rate of change of the direction of the tangent vector, of direction of the tangent vector per unit length. Because here I have taken unit speed, but if you take arbitrary curve, then essentially you have to consider the direction of the change per unit length. So essentially you divide out by the length essentially. So this we have seen, I mean, in the section of curves, we have seen, I mean, if you don't, I mean, if you have not seen, then also you can take this as the recall also. The sign curvature essentially is the rate of change of the direction of the tangent vector. Now, as I am trying to motivate you every time, that once we know the notion of the curvature, let's say in case of curves, then we would try to generalize the similar notion for surface. So now for surface, so we have to suitably change all these things, like the tangent vector or the direction, how they are measured. And now for surface, the direction is measured by what? The unit normal vector. Direction is measured by its right. So I mean, the unit normal vector, somehow this we have already seen many times, right? That's how we motivated the second definition of the second fundamental form and all the things. So it's actually reasonable to expect. So let's say it's reasonable to expect that rate of change of n, now per unit, here we had per unit length, right? So for surface we can't measure length. What we will do, we'll do per unit. Any guess?
Area.
Yes, perfect. So we'll do rate of change of n per unit area, and this should be a measure of curvature, right? That's a reasonable expectation. And now let me be little bit more precise. So now how did we compute the value of n at some points? This was the definition of the Gauss map. So in other words, we want to compute the Gauss map of some, let's say, some small region. So if this is a surface, you take some P, then you take some small region R, and that's the region G. G of R will then give you all the values of N at these points. And then you take the area of this and you compute area of R, and you take the limit and you take R shrinks to P. So essentially, that's what we'll see in later. I mean, you can take some shrinking balls containing P, and then the radius goes to 0 essentially. And this is what I was talking about, rate of change of N per unit area. So this should be somehow related to the Gaussian curvature, right? And that's exactly what Gauss also visioned, and that's the next theorem. So, sorry. Let sigma U2 R3 be a surface patch and let U0 V0 in U and consider the closed disk for delta greater than 0. R delta is set of all UV in R2 such that U minus the length is essentially less than delta square. So that's the R what I was talking about, along with center U0 and V0 and radius delta in U. Then the theorem says, then if you take limit delta goes to 0, so the balls are shrinking to the point, and you take the area, what you have learned last week to compute, of R delta with respect to N, and then you divide out by with respect to the surface patch of R delta, and this is nothing but mod K. So where K is the Gaussian curvature of sigma at the point sigma U0. Yeah. So this is, I mean, my whole point is to tell you that it's not that difficult to expect. This is exactly the same thing what I have written here, just in a bit more mathematical terms. Okay. So it's like a ratio of the area. Why I am taking the ratio? Because I am trying to compute the per unit area. That's exactly what we saw. Per unit area is given by the, then you just divide out by the ratio, and then you compute the area of the thing, ball covered by the thing, in terms of the values of N at these balls. So that's the Gauss of R. This you can get the area of this in some sense. So that's nothing non-trivial what I'm saying. And then the only thing what I am getting is the absolute value of the Gaussian curvature. Okay. So let's try to prove this. This is a very nice theorem because as we'll see in some examples, like in till now, whatever curvature we have computed, every time we had to, it's like a little bit mechanical process. We have to, without understanding the geometry, we compute all the coefficients and then you take the ratio and then you find out something without really looking at the picture. I mean, you should ask, I mean, or I should also tell that I have not really drawn that many pictures, or like I have really tried to find out what the curvature should look like. Okay, I have made some comments that, okay, for unit sphere, you have found out the curvature is 1, which is what expected. But that's exactly the term. What is expected? So expected means what? So you, for geometrically also, you should find the curvature, right? And this theorem somehow gives you one tool to find out some computations of curvature without any computation. That's what we will see in some examples and also in some exercises. Very nice exercise. Like for torus, that will be one of the exercises for you. Yeah, so let's try to prove. The proof is again a little bit mechanical. I mean, since the intuition I have already told you, the proof is essentially just going through the definition. So let's try to do that. So an of r delta divided by a sigma of r delta. This is nothing but integration over r delta norm of nu cross nv du dv, and in the denominator you have sigma u plus sigma v. This you have seen last week, right? The definition. So now you write this, we have done many times. Nu you write nu you write in terms of the linear combination of the basis vectors of the tangent vectors. So let's do this. A sigma u cross sorry, not cross, plus b sigma v cross c sigma u plus d sigma v. And now this is what? This is AD minus BC sigma u plus sigma v. This is just by the vector multiplication method. Now AD minus BC is what? This is, if you remember, this ABCD was the matrix of W. So this is determinant of W. But moreover, I can now replace W by Fi inverse F double I times sigma u plus sigma v. And what is this? This is exactly the definition of Gaussian curvature. So this is nothing but k sigma u sigma v. So let's rewrite an r sigma r delta divided by an a sigma r delta as integration over r delta mod k times sigma u sigma v du dv, and integration over r delta sigma u sigma v du dv. So it seems we are almost there, right? I mean, if you can somehow integrate this without bothering this that much, and the denominator is exactly the same, so intuitively this should only give mod k. But let's make formally what we mean by intuitively. So now you would see this kuv, this is actually a continuous function. This you will see in the exercise. So since this is a continuous function, now this is kind of an analysis problem. So one can now choose, it's a limit problem essentially. So one can choose delta positive small such that mod k u v minus k u naught v naught is less than epsilon for some small, some positive epsilon. Okay, and this gives you actually a kind of a triangle inequality. U naught V naught minus epsilon less than mod K U V less than U naught V naught plus epsilon. Yeah, this is why, because as mod A minus B is greater or equal to mod A minus B. So this is nice. Why do we need this? Because now you put this in the integral, and if you put that, then what you get is nothing but mod K mod K U naught V naught minus epsilon less than A n R delta A n A sigma R delta is less than mod K U naught V naught plus epsilon. So if you essentially if you take the limit, this implies that mod A n R delta divided by A sigma R delta minus K U naught V naught is less than epsilon. So we are done. So essentially it converges to mod K. The limit exists, and then we are done. Okay, so finally, what we heuristically what we said, that the ratio of area of G of R divided by area of R, that's exactly what we have written here. This should give you the absolute value of the Gaussian curvature. And the proof is, as I was telling you, it's we just write the definition at first, and then again this technique we have done now many times. Nu is, what is Nu? Nu is like a vector in the plane of generated by sigma u and sigma v, because Nu is perpendicular to n, and you have a basis of R3 which is sigma u, sigma v, and n. So that should be a linear combination of these two. And then A, B, C, D we took as a map from the Weingarten map, and that's again today this is what we started with, and that's exactly the Gaussian curvature. Okay, so if you think of this Nu, Nv, and this K times sigma u cross sigma v, so essentially what you are seeing actually here, this part is kind of the Gaussian curvature times the denominator, and that's why exactly we are getting the absolute value of, I mean the mod K. So that's fine. I mean, if you want to compute the sign, that can be recovered. That's the next thing. So sign can be recovered from Gauss map, and you can define the signed area of GR as plus minus ANR, where the plus minus are according to, so you just give an orientation essentially, whether NU cross NV points in the, so if they points in the same direction as N, in the same direction or opposite to N, right? So again, I mean, this NU cross NV, that's like a perpendicular to both NU and NV. So then it's like you have either towards N or to minus N. So if it's towards N, then you term this as plus, and if it's towards minus, then it's towards opposite side of N, then it's minus. So essentially what I am saying, you can actually get this result that the Gaussian curvature is nothing but limit to send the balls to the point, and in the numerator you take signed area of G of R, and in the denominator you just take area of. So that should give you the whole definition. And again, this is not surprising, right? Because let's come back to our motivating example, the curve, and you see here we were finding out the sine curvature. So that's exactly what we have found out here. So it's nothing different from what we have seen. It's kind of the generalization of the same. Again, see here we told that that's the sine curvature. So essentially what we are finding out, that the Gaussian curvature is also, we have to use the sine area. Otherwise there is a sign ambiguity. Okay. So in the last 4 or 5 minutes, let me just give out some examples where I told you that you can compute some Gaussian curvatures where you don't need to even compute anything. Yeah. So let's first again do the same things for the same examples again. So let's consider S to be plane. So once you consider S to be a plane, then the unit normal, this is constant, right? So that means what? If you take any, let's say closed disk R, or any small ball here, closed R, then G of R is nothing but a point actually, because N is constant at N. And since this is true, that means what? The area is, so it has zero area. And this means what? The Gaussian curvature is zero. Is the logic clear? I mean, it's like very immediately. I mean, here you should really remember this motivating example. I mean, what I said. Yeah. This rate of change of N per unit area. That's exactly what I am saying. So what I'm saying is, you have the mathematical formula, but you understand the formula in terms of this, the rate of change of N per unit area. And that's exactly what I'm computing in terms of a plane. So when you have, so for any R, then G of R will be always a point by definition. And for a point, you have zero area. So then you are done. And let's consider the unit sphere then. So let's S to be the unit sphere. So here, the unit normal at P in S2, this is parallel to the radius, right? And parallel to the radius vector from the center to P, essentially, from the center to P. That's just by definition of the unit normal. But that means what? If it is the case for every point, then that means what? Your Gauss map is essentially identity with a sign. So either it's an identity or like a negative of the identity, and sometimes it's called antipodal. So based on the orientation, right? I mean, essentially you should understand the Gauss map is essentially identity. I mean, either plus or minus. If this is identity, then these maps are equiareal. I mean, like, so if this map will send the same area to same area, right? Because this is only identity. And that means what? This, I mean, here in the formula, yeah, here itself. I mean, the signed area of GR, if G is identity, and this is, and both of them are same. So essentially what you obtained is mod K is 1. Now we have to only figure out what's the sign. So if sigma is any surface patch, so we'll check as the definition I suggested what is signed area. So let's say if sigma is any surface patch of S2, so then we actually have n is plus minus sigma with, you can see this with both choice of nu cross n, sigma is sigma u, sigma v. So this actually means even if it plus or minus, it will be the same thing in some sense, then k will be equal. So then we are done. So now you see, I mean, for proving this k equal to 1, let's come back to the example here, what we have also computed. Yeah, see, here also we have computed, and that needed much computation, right? So this was really a novelty of Gauss's intuition, that without almost, I mean, it's almost for free, you are getting the curvature of a unit sphere. And later you would, I mean, in the exercise, you would find out for torus, for example, you can also use the formula, this one, to compute the Gaussian curvature. And similarly for many others. So essentially what I will just end with this comment that next lecture we would see some more components of Gaussian curvature, which are called principal curvatures. And then finally we'll end this week with some kind of classification with how the Gaussian curvature determines the shape of a surface, like when it's positive, what kind of surface we obtain, what when it's 0, when it's constant, when it's positive, all sorts of things. Yeah, and then I will stop. Please ask me any questions, doubts, if you have any.